And this is the controller.
Good afternoon. My name is Mutlu Rahman. I'm from INTCEC2025 University, and my research interest actually work on renewable energy and smart grids. And my mentor is Dr. Mahmoud Hassan. And today we are going to talk about the inertia things that really lacks in DC magnetic system. Actually, my one is really different from the rest of the work presented in here. Let's see. So this is my title: Reintroducing rotational inertia in microgrids, stability enhancement using BLDC and synchronous generator. So these are the table of contents of my presentation that I'm going to follow through the session. From introduction to the conclusion. Okay. So what do we see in here? We see just the moon, some black buildings, something like that. So it's a blackout condition. In 2021, there was a blackout in Texas, and it affected more than 10 million people. So there was a problem in the grid system, and it cost like $130 billion losses only in Texas. So what happened in the grid system actually? So in the DC microgrid system, we use inverters that actually provide some virtual inertia, and there was a mismatch between the inverters of different microgrids, and it actually led to a blackout. So these are some terminology that I use in my presentation, like BLDC motor. It's just a DC motor that is commutated, electronically commutated. And synchronous generator is actually available in almost every power plant, and it has a big rotor, and that rotor actually provides the inertia of the system. Even if you don't have any fuel for some moments, it can still provide the power to the grid system because of the inertia of the rotor. So inertia is we can feel it even in the when we drive. When we push a brake, we move forward because of the inertia. Though the vehicle is stopping, but we're still moving. This is something like that. So rotational inertia is kind of physical inertia, and virtual inertia is something that is not actually a real one. We create the inertia in the DC microgrid system to feel like a generator, to provide the feelings to the grid system as a generator. It's done by the power electronic circuitry and with the energy storage system. So this is the energy trend throughout the world, and you can see that renewable energy actually going up more than 45% nowadays throughout the world. That's really amazing because it's nice to see, and it's a good sign for the sustainability of sustainability, but it has some technical challenges that we need to solve. So what are the challenges? Challenges are like if you see on the PV panel, there is no rotating part. Even if the sun is down for a second, there will be no power. But on the other hand, the conventional grid system, even there is a moving part in there. So even if you don't have fuel for a second or for a minute, it will still supply some power to the grid before it falling apart. So the photovoltaic panels, they don't provide any inertia support, but the conventional grid system has some inertia support. And with increasing penetration of the renewable energy sources, we are getting reduced system inertia. So with reduced system inertia, the frequency will deviate and the frequency deviation will lead to the blackout, and the blackout means unreliable system, so we don't want that. The existing solutions like batteries, flywheels, they provide virtual inertia, but sometimes they are costly, complex, or inefficient, or sometimes they don't actually provide the real inertia. So it's not comparable to the real inertia one. So there are some gap between the goal and the present situation, like synchronization issue. We need to, if you use an inverter, then we'll have to work on with the synchronization, and renewable energy and renewable sources actually don't have inertia, so we need to work on that too. And we already said that virtual inertia is not as effective as the physical inertia. So our objective is to introduce some inertia into the system and providing AC output power without inverter. So these are the key elements or key concepts of our proposed system, like rotational inertia, that is a kinetic energy stored in the rotor of the synchronous generator, BLDC motor that is highly efficient and is actually convert the DC to mechanical energy. As synchronous generator, it converts the mechanical energy to alternating current power. So in our system, we have the solar PV panel that is connected through the MPPT. It connects to the BLDC motor, and the BLDC motor is connected to the synchronous generator, and that generator actually provide the AC output power. So we are actually providing the DC power and getting the AC power from the system. So we are actually converting the DC to AC without the inverter. So this is the conceptual block diagram that we have used in our simulation, and we have forwarding panel, and we used MPPT, and in that MPPT we used actually part of an observation method, and our MPPT is connected to the BLDC motor, and that BLDC motor shaft is connected to the synchronous machine. In here is synchronous generator through the coupler, and that synchronous generator is providing the AC power and supply to the load. And in between there is a controller that actually controls the speed of the rotor, and it is very crucial for the system. So in our simulation setup, we used MATLAB Simulink 2023, and we have also used the photovoltaic panel that have 360 watt power, and our solar panel ran on a 1000 watt per meter square solar irradiation, and the temperature was 25 degrees centigrade. So these are the output that we get from the synchronous machine. So we see that within 30 seconds our system gets stabilized, means it providing stable power to the load. And this is just the zoom version of that graph, and we see that the frequency and the voltage are very stable, and it's a pure sine wave. So it's very a good sine wave for the as an output power. And this is the speed of the rotor. Within 50 seconds, the rotor speed actually becomes stable, and from 0 second to 50 seconds, it takes time to get the rotation. That means we have some inertia that takes the rotor to become stable. So from this graph, it's very clear that there is some inertial support in the rotor. Even if we have the no power, then we still have some time, like for a couple of seconds before power runs out. This is the input power and the output power that we provide into the system. and you can see the power becomes stable, the input and the output one at the point, and stable for the whole time after that. And this is the efficiency graph that we got from the our simulation, and we can see that the efficiency is more than 80%, which is very good, because though the inverter's efficiency is more than that, but the inverters don't have inertia. But in our system, we will have some inertia. So that's the trade-off between the inertia and the efficiency. So there are some alternatives in the already available in the market, like supercapacitor, which is very fast in response, but it has some issues like it's highly it's very expensive, and it doesn't support inertia actually, and it's pretty low. On the other hand, lithium batteries, it provides moderate efficiency, but it's highly complex. But in our proposed system, we use the BLDC and synchronous generator chain, where we have some real inertia and moderate efficiency and moderate cost. So the challenge we faced actually stabilizing the rotor speed, because our synchronous generator rotor and the BLDC rotor shaft are coupled. If there is any change in the speed of the BLDC motor rotor, then the frequency of the grid system will change. And we always face the challenge, like if we put a load, or if we remove any load from the grid, then there is a feedback system in our simulation that stable the frequency. But we still need to work on that, because sometimes the frequency goes beyond the standard limit. So it's a real challenge. And another thing, this is just a simulation, so experimental validation is required. So in conclusion, we can say that our system has some real inertia that really beneficial for the microgrid, and we achieve the AC power without inverter, and it's a balance between the efficiency and the stability. So I think I hope it will be helpful for the DC microgrid application in the future. And I want to thank to the College of Engineering and Computer Science of Anand University and Research and Technology Transfer grant for their funding. And this is the floor for the question and answer session. So if you have a question,
Okay, thank you very much. Questions? Yes, please.
So validation is very important for engineering. We know this. How are you going to validate what would be the system that you're going to set up? In lab scale or really in real
no, in a lab scale first. So
What were the components?
It-
Particular
yeah, the
hardware part.
hardware.
Hardware. What kind of
Oh,
hardware
the
components?
hardware. I already mentioned the hardware, like we use some PV panel that's readily available in the market. BLDC motor is available, but we need to customize that. And some MPPT algorithm is also available, so you can surely use that. But and the problem is the main challenge is the coupling of the mechanical power and the electrical power. That's our challenge. But it will work, but still the energy transfer need to be efficient. Otherwise, we lose some efficiency of our system. So the parts like BLDC motor, the solar panel, synchronous generator, is readily available in the market. So we can actually assemble the things in the lab first.
Yeah, actually, I have one question. Is this kind of blackout problems? The main issue can be about the amplitude, but the second very important issue is the frequency.
Yes.
Because the stability of the
It
frequency
depends
is
the
very
frequency,
important.
yeah.
So, do you have, for the application in the future, do you have any idea to stabilize the frequency Because you said that you have still high inertia.
Right.
So that is, I think, a very bad problem. So how can you decrease this time, I mean, for the inertia, and also the frequency stability? Do you have any idea? Because
Okay, so
that's the main problem.
frequency stability is the main issue for the blackout. The blackout actually happened because of the unstable frequency. In USA, we use 60 Hz, 60 Hz power line. So that means we have to maintain the frequency between 59.5 to 60.5. That means it's very strict. If we go below this range or by crossing the range of 60.5, then the grid won't be able to synchronize the system. So it has to reduce the load. This means cut off the power from the grid, or it has to shut down some power plants. So frequencies in our system, frequency stability depends on the speed of the rotor. So if we can maintain the constant frequency of the rotor, I mean BLDC motor, then it's not an issue. So in our system, we can actually control the BLDC motor. Actually, we need to develop a controlling system for the BLDC motor. We developed one, but it has some issue that we need to actually find out. So if we have a controller that can maintain the speed of the rotor at a constant speed, that means we will get a constant frequency from the AC synchronous generator.
So you need also powerful sensors for that.
Yeah, we have some Hall sensor for that. Yeah.
Okay, thank you. Any other question? Yes, please.
What about cross-country frequency synchronization? Let's say US and Canada, US and Mexico. This main problem, as you said before.
Yeah.
Frequency synchronization.
Okay. Actually, in North America, all of the actually your mentioned countries all is the same frequency. In our region, like in Asia, we use 50 Hz. In this North America region, they use 60 Hz and 110 volt. So, if you want to actually cross synchronization between the countries, you have to be in the same range. Actually, 50 Hz and 60 Hz, it can be actually cross connected. So in Canada and USA, they all use the same frequency, so it's possible.
Okay, thank you very much. So we can make a choose.
Yes.
Okay, thanks. So we go to the second presentation for this session. 145, considering bulk data centers in hybrid AC/DC transmission network expansion planning, by Mustafa Ananch. The name, how can you pronounce it? Your name?
Mujtaba is correct.
Mujtaba, right?
Yes, Mujtaba
Ah,
Ahanch.
okay, okay.
This is, yeah. All right. And here we go. Okay. Yes. Good.
Okay. Hello everyone, my name is Mujtaba Ahanch. I'm a PhD student right now at the University of Arkansas, Electrical Engineering Department. Today I'm going to give a presentation on our latest research on transmission expansion planning. Actually, considering bulk data centers in hybrid AC-DC transmission network expansion planning. This project is supported by NSF Center for Grid Connected Advanced Power Electronic Systems, or GRAPES, located at University of Arkansas. Okay, so transmission expansion planning is one of the fundamental aspects of power system planning. Transmission expansion planning, TEP, ensures reliable power system operation while meeting predicted load growth. Successful transmission expansion planning actually tries to find the most efficient and affordable expansion plans to guarantee reliable power transfer from generation site to load centers. So, as you know, nowadays we are facing new challenges. Actually, we are seeing new technologies, inverter-based energy resources, advanced technologies such as flexible AC/DC transmission systems, bulk data centers, and microgrids that was presented before this presentation. These new technologies can bring about new challenges to power system operation, mainly because generation side is far from the load centers. So we need to add new lines to our system, and it requires new strategies to meet the future demand, considering the existing or new challenges in power system. So transmission expansion planning can be defined as a master transmission problem, including 4 sub-problems. The first and foremost is about investment. We are trying to minimize the installation cost of new equipment, new lines, transformers, facts, converters. The second sub-problem is about the resiliency. We try to improve the resiliency of the system. The second sub-problem that is usually ignored in transmission expansion planning problems is about stability of the system, voltage and transient stability. And the last one is about uncertainty of renewable energy resources. So these sub-problems can define the master transmission problems that we are considering in our project. So I'm sure you have seen these 2 structures. On the right side, conventional AC transmission towers, and on the left side, HVDC transmission lines. So these new structures are going to replace the conventional AC transmission lines, transmission towers with 3 lines. We are going to have transmission lines, transmission towers. So these new towers can bring about new advantages for power system operation. They can reduce financial investment and overall planning costs. They can decrease power losses. That's very important in power system operation. They can relieve transmission congestion and some other technical and environmental advantages. So transmission expansion planning problem considering high voltage AC DC networks can be defined as an optimization problem, including an objective function and some constraints. So the objective function itself can include some different terms. For example, the first one is about the installation cost of conventional AC transmission lines, transformers, cables, and circuit breakers, and the other equipment. The second term deals with the installation cost of HVDC equipment, including HVDC cables, converters, DC circuit breakers, and so on. And the last term is about power losses in transmission lines. So for our research, we are considering these 3 terms, but other terms can also be included in this objective function. So about constraints, these are the conventional constraints in transmission expansion planning optimization problem. The first one is about power balance constraints. there should always be a balance between generation and demand. The second constraint is about power generation. Any generator has some limits, generation limits, and the other limitations is about voltage limits and power line limits, and this equation also represents the power losses that is obtained after running power flow in our problem. So the hybrid AC-DC transmission lines require new power flow techniques. I mean, the existing power flow techniques that we use for power system analysis, they are no longer valid because we have DC equipment, DC lines, so we need to update, actually enhance our power flow techniques. So in this research, we use a sequential method for AC-DC power flow, actually hybrid AC-DC power flow. Based on this method, in the hybrid AC-DC system, one of the converters of the system is considered as a DC slack bus, and the other converters are considered as constant P control bus. Then we run AC power flow based on the DC slack bus that we already defined. After finding the AC side voltages and power injected to the system, then we are able to find the DC parameters, including voltages and powers. So to solve the optimization problem, there are a variety of techniques, exact methods. On the other side, we have meta-heuristic optimization techniques. We have tried both techniques, but for this research, specifically, we use PSO. I'm sure you have heard about this new optimization techniques. They are very simple. The idea behind PSO or population-based techniques are very simple. Actually, a group of particles navigate through a problem's solution space to find the best solution. So each particle adjusts its position based on its own best known solution and the best solution discovered by the entire group. So after repeating some loops, we are able to find the best solution for the optimization problem. So the novelty of our research is about considering bulk data centers in transmission expansion planning. This figure represents an estimation of the total electricity consumption of data centers in the United States from 2014 through 2028. So this estimation includes mainly the servers, data servers, storage technologies, energy storage technologies, network devices, and the other associated infrastructure. So from 2023 through 2028, a range of scenarios have been proposed for projecting data center demands. These scenarios are mainly based upon the main data center sector players, including AI hardware, graphic processing units, accelerated servers, manufacturers' capability in providing the market demand, and shipment issue. These are very important factors that can impact the projection. So the projected scenarios range from 6.7% to 12% of total United States electricity consumption until 2028. So that's huge for power system management, actually for power system planning. So 12% can be considered as the worst case scenario for long-term power system planning. So a variety of configuration have been proposed for connecting data centers to the AC, to the power systems. So here I provided just two common configuration. On the left side, we have a typical data center connected to AC networks. This is a conventional topology. We have AC transformers, we have data centers connected to the network through DC AC converters. But on the right side, we have typical data centers connected to DC networks. This is a new configuration. So based on this configuration, we no longer use transformers. We are able to connect data centers directly to the DC network. So if we have a DC line in our power system, so we can connect the data centers directly to those DC lines through DC-DC converters. So it is said that these topology is more efficient and it can bring about new advantages for power system operators. So we are considering both configuration in our study. So this is the resilient transmission expansion planning software that we are developing right now. This is the GUI. Actually, this is the previous version. We are developing it, and hopefully we can present it later in another conference. So we have better features. But for now, as you can see, transmission expansion planning GUI includes the algorithm, the optimization technique that we can select. So we can select meta-heuristic techniques such as PSO, or we can use Mothic, Ruby, the well-known solvers in the market. So the second option is about transmission expansion planning type. It can be AC, pure DC, AC, DC, multi-period AC transmission expansion planning, multi-period DC transmission expansion planning, or multi-period AC, DC transmission expansion planning. The other option is about cost function. As I mentioned, we have different sub-problems. We can select either of them, or we can select all of them for our analysis. The other one is about the cases. We can use IEEE standard cases, 9 buses, 14 buses, 39 buses, or we can create our own network. So if we have information, or we can receive information from utilities, we are able to create our own network and then implement transmission expansion planning for the new networks. And finally, we can run the program and we can see the results. The lines that have been selected can be shown on this GUI. So we implemented our framework, transmission expansion planning framework on IEEE 6-bus system known as Garver system. Actually, we modified the network. We added 2 buses with converters. So for the first scenario, actually this system, 6-bus system, has 6 AC buses, 5 AC lines, 1 DC line, and 2 converters. The maximum generation capacity is around 530 megawatt, while the total active load is 760 megawatt. So transmission expansion planning strategy tries to find the best options to connect this generation bus to the rest of the network. So that's the goal of this framework transmission expansion planning problem. In the first scenario, we didn't consider data centers and energy storage systems. We just run the program to see the results based on the existing lines and the new lines that can be added to the network. So as you can see, the program suggested 2 types of lines. Red lines represents the new HVDC lines, and the blue one is the new HVAC lines. So it's a hybrid AC-DC transmission expansion plan. In the second scenario, we added a data center. Actually, it's a 50 megawatt DC data center added to bus 4. So we run the program again to see the results. In this scenario, again, we have 2 DC lines and 1 DC converter. Besides, the program converts the AC, conventional AC transmission line to DC, high voltage DC line with a converter. And the third scenario, in this scenario we added 2 energy storage system at bus 5 and bus 2. We considered the worst case scenario for the energy storage system, but a variety of scenarios can be considered for energy storage system. But for this study, we just wanted to see the impacts of the energy storage system. So it's just about the worst case scenario. In this scenario, the energy storage system should be preserved throughout the transmission expansion plan. So as you can see, in this scenario, the program proposed 4 DC transmission lines with some converters, and we don't have any AC transmission line. So here you can see the energy storage specification we used for this study. 2 energy storage systems with almost the same features, same capacity, the same charge rate, discharge rate, and different charge and discharge efficiency. And this table also represents the results of the new lines that have been added to the system in the third in all the scenarios, the type of the lines, the converters that have been added, the installation cost, operation cost, and total cost. So as I mentioned, this is an ongoing project. We are working on new features. We are trying to implement new ideas. We are working on a variety of networks. IEEE, for example, 39 is a very complicated network with so many transmission lines with different kind of loads. So for future studies or ongoing studies, we are trying to add, actually consider FACTS devices in transmission expansion planning. These new technologies are very important. They can enhance the performance of the power systems. They can reduce power system losses, improve the resilience of the system, the stability of the system, and they can actually help reduce the power losses. So we are trying to consider those technologies in our transmission expansion planning. Then we are trying to combine transmission expansion planning and generation expansion planning. Actually, in this study, we can consider both transmission expansion planning, as we did in this research, and we can actually find the best location for, or find the optimal capacity of generators in our system. Then we can develop the energy storage system modules for transmission expansion planning. As I mentioned, we considered the most conservative scenario for this research, but a variety of scenarios can be considered for energy storage systems, different technologies, batteries, or other storage systems can be considered for transmission expansion planning. Another research could be considering combined transmission expansion planning and gas network planning. Actually, we can see the impact of gas networks on transmission expansion planning, considering energy storage systems, data centers, or vice versa. We can see the impacts of transmission expansion planning on gas network planning. Besides, we are thinking of using AI techniques, Q-learning, the other techniques for transmission expansion planning to predict the load demand, to consider the impacts of data centers with different models in transmission expansion planning, and we are thinking of developing bulk data center models. Right now, we are seeing bulk data centers at large loads, but these data centers they have different technologies. They include AC, DC loads, so we can categorize those loads. We can define new scenarios for bulk data centers. And last but not least, we are developing the software. Hopefully, we can enhance some features, and we are thinking of releasing free open source transmission expansion planning to receive feedbacks from the other researchers. And here is the list of references we have used, and thank you for your attention. If you have any question, I will be so happy to answer.
Yeah, questions? Thank you. Yes, please.
Yeah, I know what you're doing, Mr. So for the optimization problem, how big is it? Like, you're using meta-heuristic algorithms. Do you need to do that? Can't you do it exactly? Of course, I think you cannot do that. I mean, what is the scale of your problem that triggers you to use PSO or
Actually, we have used different meta-heuristic techniques, compared the results, genetic optimization algorithm, PSO, genetic optimization algorithm, and about this problem for IEEE 6-bus system, it's not that much big actually.
Right, actually
Yeah, this is a small scale network. We just wanted to show the impacts of data centers. We just wanted to present the idea behind considering data centers and energy storage systems. But for the research that we are doing right now on IEEE 39 system, this is a very large network with so many lines, with many generators, so many loads. So for that case, we are thinking of using exact methods. Right now, we have access to Ruby, MOSEC optimization, actually the academic version. So I think we are able to handle the optimization problem using those techniques. But for now, PSO is good. The results better than.
Is your optimization problem mixed integer programming?
Yes, nonlinear.
Nonlinear, right?
Yes. Yeah, because of the power flow constraints, it's a mixed integer nonlinear optimization problem. So because of that, PSO is efficient. Yeah, it's capable of solving this problem. Maybe 4 or 5 minutes for the scale of this problem. It's efficient, and for research papers, it's good. But for the software that we are developing, we are trying to use MOSEC, Ruby, the academic version, and hopefully we can get some funds to use the commercial version as well.
Thank you.
Other questions? What about, you mentioned about 2 scenarios. What about the cost of this scenario? I mean, do you have
If I go
any
back,
idea when we compare the cost of
the coefficients, I mean the values that we use for this study are based on some references, very old references, but these are like benchmark networks, so we can't rely on these values for now. It's about $23 million. So, but if you want to be more realistic, we need to update these values. These values go back to maybe 15, 20 years ago. So, but because these are the network 6-bus governed network is a benchmark for planning. So we actually decided to use 6 bus network for this study, but for future studies, we are trying to use updated
Yeah.
values. I mean, the cost for installation cost of specifically for installation cost of DC equipment, transmission networks, so like converters. They are expensive, and the values, the coefficients need to be updated. So yeah, but based on the existing network, the benchmark, these are the installation costs, operation costs, and total cost, all in $1 million.
So now we can give your certificate. Thank you very much.
Thank you so much.
Yes,
Thank you so much.
So this is last physical. Okay, structural strain-based feedback control for a site-specific mechanical reading system by the group of Süleyman Eşkabilov. Yes, please. It's your turn now.
This is also, I think so. So, yeah.
So, good afternoon. This is Shafi Muhammad Ishtiaq. I am from NDSU and I am a PhD student. I am very happy to share some of my research here. So, my research topic is structural strain-based feedback control for a site-specific mechanical reading system. So, Dr. Sulaiman already told about the site-specific mechanical reading robot. So, weeds are harmful for agriculture, and Dr. Sulaiman already explained how weeds are harming the agriculture and what is the annual losses, and also why we need alternatives of the herbicides. So there are herbicide-resistant weeds that's popping up, so we need alternatives. So this is the robot. So we developed this for mechanical weeding, and this is the mechanical weeding system. So this is a 3-row mechanical weeding system, but this is modular and expandable, and we use 3 linear actuators to control the delaying operation. So the robot has different autonomous operation. One of them is road detection, navigation, and another is weed detection, prescription weed map generation, and site-specific weeding by QLS. So in the weed map, so the robot actually delays in the specific feed where the weeds are present. So this is how it removes the weed in the specific location, and we use the GPS location for the weed cells to actuate the actuators for delaying. So the challenges for this operation is like operational blockage. So when the robots delays in the field, so there are stones or hard soils, so it can be blocked, and it can make damage to the system, and also it can make the robot stop. So this is the one kind of hard soil that can make the robot stop, while if the three actuators goes down and 3 sweeps can 1 to 2 days together, that can be a possible operational blockage. So how we want to solve that? So the simple solution, we can take the strain, structural strain, as the parameter to detect the blockage. Like when the sweep hit the soil, there will be change of structural strain in the shanks. So if we can measure that and we can say that threshold value for that, we can control, we can detect the blockage. So this is how it will work. So when it will it will hit a rock or hard surface, there will be a threshold strain, and when the threshold strain will cross, the actuator will retract back to avoid the stoppage and operational blockage. So for the structural strain, we performed finite element analysis of the shank, and we detect the maximum strain concentration in the shank. So, and in that location, we install strain gauge sensor. So this sensor detects the strain, which we can use for detecting the blockage, and we used a DuSoft data aggregation system for measuring the strain for the shank. So this is the control system diagram. So as it is simple to take the strain and detect the blockage situation, but if we want to make it robust and really operational in the field, we need to consider other more parameters like vehicle speed, the wheel torque, etc. So in the laboratory test, we performed some actuator pattern to hit the hard surface and record the strain data, so we can figure it out what could be the threshold strain and how could be the strain behavior. And we controlled it automatically by feedback controls. We also performed field test, and in the field test we also added distance laser distance sensor to measure the actuator stroke, so we can analyze the movement of the shank with the strain. So we can compare them both to identify what is actually happening there. So this is our laboratory test data. So this pattern we applied in the laboratory test. This is the actuator position, actuator on and off. We did this pattern and we get this strain data for that. And later on we applied that for controlling the actuator from that strain data, and we set a threshold value for that. And the orange one is the strain data for not activating the control, and the blue line is the data for with activating the control system, feedback control system. So we can see when the threshold is crossed, the system goes down. And this is the field test data we applied in the field test. So when the actuator extends, we can see a strain deviation that proves the friction with the soil and the sweep. So in the conclusion, we can say that there should be a threshold range for the strain that will detect the blockage, and the strain data needed to be integrated with GPS data and UGV speed, and also dynamic calibration is required for this process, because there could be different soil types. So for hard and clay soils, different kinds of soils can have different threshold range. Also, strain gauge sensors are sensitive to humidity, temperature, and physical damage. So we need to be isolated from those things. And in the future studies, we will implement load, torque, and laser distance sensor to make it more robust and applicable for the practical situation. These are the reference, and this project is funded by USDA and IFA. Thank you, and this is our lab website. Welcome to visit.
Thank you very much. So questions, please. Yes, please.
So you studied the stress analysis in the system. You studied like how much stress you can apply to the motor itself, like the actuator, what is it? You just studied the system of the method part. You studied the shaft and the rest of the system of the actuator.
So you're talking about how much load the actuator can absorb.
But it's still also like even the shaft and the actuator itself.
Yeah, we selected the actuator like that. We know its load capacity, so it's in safe side.
Okay. And still keeping the shaft itself.
Yeah.
Enjoy.
Thank you for the presentation. What about the feedback sensor? Is there any other options for the sensor? Not only laser sensor, maybe other types of sensors. Let's say magnet sensors inside of this actuator, measure capacity sensors.
Yeah, we have different kind of options instead of laser sensor. Like we also get data from the linear actuator itself because it's a canvas controlled actuator. So we get the position feedback from that, and yeah, we can also apply another sensor for that. What is it? Magnet sensor.
So why do you need laser sensor if you have?
Yeah. Because actually we don't know the actuator feedback is correct or not. That's why we installed laser sensor.
It's for
validation and compared it with the strain gauge sensor, because strain gauge sensor we are taking data in the data acquisition system, but the linear actuator giving data to the controller. So for validating our system, we install the laser sensor.
We can collect from one sensor into the two data nodes. It's not only for the sensor, but also for data acquisition. It's impossible, like two masters.
Yeah, we can integrate it. Then we have to take the canvas data to the data acquisition system and read that. The problem is the canvas had a low frequency of data, like it takes 2 or 3 data per second. But in the laser sensor and the strain gauge sensor, we are using 10 Hz. So it's a little bit low in the canvas. So that's why we prefer to use laser sensor to validate our concept. But in the control, there is no need to use this laser sensor. That is for.
There is no other options of protocols for the feedback sensor. Only can.
For the actuators. Yeah, we can use other sensors, and also we can add the linear actuator feedback to the data acquisition system. But then we need another module for that. And we have the option of laser sensors, so we validate it with that. But we will work more.
What if there is very cross, if it will be between the laser?
Oh, the laser sensor is only for validation. It's not helping to the control system. It's just for our testing and presenting the results, not in the control system. The control system is work on the actuator feedback.
Okay. Yes,
Since
please.
you just discussed the sensor also, like you can use it for like it's just an idea like for data generation in the future. Like if you have a map for the field, where's the rocks and things that block the reading process, you can actually do a map and save that map for future work. Like especially like sometimes you will have like metals and a lot of huge stuff in the field. You can actually have that map that tells the robot where these things like exactly, and then you can avoid them in the future while you are doing the mapping or something. So the sensor actually could be used for this kind of data generation as well.
Yeah, but it can be changed. Like when you grow the crops, it's glazing happens, so rock can be shifted, and also when it get dry, it become more strong,
Yeah.
hard. So yeah, we can say that, but it's not constant actually. So
Yes.
What about the RTK stations? Can you use RTK stations instead of GPS?
yeah, we can use that, but as far as this GPS has a good, I mean, it's giving 2 centimeter of accuracy, so it's enough for us. So that's why, as it is integrated with the robot brain, so we are using that now. But alternatives.
Yes, you will say something, I think.
Can I add to the?
Yeah, sure. He is actually working on that thing.
So actually we are using the RTK, and the RTK corrects the GPS reading and make it like accurate.
Okay. Thanks.
So, any other questions? I think no. Thank you very much, Shafi. So we can congratulate you for this fantastic presentation.
Yes.
So, thank you very much.
You're welcome.
Okay, so actually this is coffee break time, but I can also close right now with the coffee break together. So this year we have an acceptance ratio of around 40%. I mean, when we compare with all the papers, 40% acceptance ratio is very good. Because if it comes to law, and it means that you have much more qualified papers which we have received in our conference. And I, as the last word, I would like to remind you that please share your participation certificate in the social media to make the advertisement of this conference. Just put the photo of your certificate, or maybe if you have own photos while you are presenting your work, or and then for video maybe in social media, if you can share, we will be very happy to also advertise the conference for the next year, because our aim is to have much more high qualified papers. And as you may see today, we had a very broad topics, from power electronics to agricultural applications, but all included computer and computer sciences, and also electricity together. So this is our aim. So therefore our conference topic is focused on electrics and computers and interdisciplinary. Some of the, for instance, last year we had many medical applications on electrics and computer also, together with medical applications. So this kind of interdisciplinary approach is very important, not only for the industry, but for the medicine sector, pharmacy sector, and other also other industrial sectors. So that's a very important issue. Our aim is to make much more complete works in the future. So therefore I am happy to be with you here, and thank you very much for your contribution to this event, and we hope to have for the next year, we hope to have much more well-qualified papers
better papers than this year. Thank you very much. And please, in the questionnaire form, in the QR code, please write your thoughts, and also we can have these ideas to make much more better events. And at 6 o'clock we have gala dinner. It is not too far away from here, but with a car you can go to the Turquoise restaurant and cafe. That will be a very good dinner, because yesterday we have checked the restaurant, and we had a very good menu for you, and we hope to have all of you there, so we can somehow discuss much more detail, maybe the questions and so on. We can have much more time there in the dinner time to discuss the matters. Thank you very much. If you have something to add right now or share with the audience, you can also talk. So this is not only for me, this is a discussion forum. If you have any idea, or yes, please.
Is there any evaluation
Yep.
for the physical sessions?
Yeah, this is the evolution. Yeah, and we will also okay. This year we also initiated the best paper awards. If maybe a few days later, we will put the winners on the website of the conference, and I will also write a CMT email to all the authors, because we have 4 main tracks for this conference, and for each tracks we have best paper award. So we will announce this best paper awards too. And what is the award? 50% of the next conference's registration rate will be
Discounted.
Yeah, discounted 50%, so half of the. So that's a good number indeed. But we hope that in the future we will also promote much more. I hope to improve, because that's good to have young people here, and that's very good to cooperate with young people and discuss the science and technology and the applications. So thank you very much for your contribution, and see you in gala dinner also. Okay, so we can have some coffee.
What about group photo?
Yeah, we can make group photo. Why not? So
Exactly.
where can we? Maybe on the upstairs. Can
Yeah, I can. I think so, because in the upstairs we have a like a big
yeah,
poster.
we have a big advertisement.
Yes, and we can.
Then maybe we can make a group photo.
Yes.
Yeah.
Yeah. Okay.